Approximately 4 minutes remaining. Approximately 2 minutes remaining. In the last remaining minute, please provide as much work as possible such that I can assign partial credit, and make sure you've written everything that you'd want scored, and then I'll be coming by to collect in approximately 1 minute. Okay, I'll be coming around to collect. Please pass your papers up. And as long as you're set up there, I'll be. Thank you. Thank you. Thank you. Okay, so just a few things to note here. One of the better ways to prepare for the quiz and to prepare for the lecture is to complete the homework and, most importantly, complete the pre-lecture assignments. These are assignments that are due at the beginning of each lecture session that are designed to help you structure your reading of the textbook and structure your reading of the notes and slides to better prepare for the lecture content today. You see these periodically on Canvas, and you'll have a pre-lecture assignment for every single lecture session. So make sure you're keeping on top with those and keeping up with the reading for this class. With that out of the way, I'll have these scored and entered into Canvas momentarily, but let's talk a little bit about the solution to this quiz. So first and foremost, remember how I had everyone and I suggested that everyone memorize the metric prefixes? These are critical for your success in this class, especially for writing proper lab reports. So first and foremost, we were asked to convert 375 milligrams to micrograms. Okay, let's write out our basic prefix to base unit conversion. So we know that 1 milligram is equal to how many grams? What does the milli prefix correspond to? Yep, 10 to the negative third. Okay, we also know that let me go over one more space. We also know that 1 microgram corresponds to how many grams? Negative 6. Micro is 10 to the negative 6. Okay, so with these equalities established, looking at our desired unit conversion, our goal is to go from milligrams to micrograms. And what intermediate unit are we going to go through? Grams. Okay. So starting off, we have 375 milligrams. And my question to all of you is, in order for us to end up with grams as our final units, what units need to be on top of this equality? Grams. Okay, so we're going to put grams on top. And in order for milligrams to cancel, what units need to be on the bottom? Milligrams. Okay. Now, all we have to do is copy from this equality. So how many grams are in 1 milligram? Yep, 10 to the negative third. Okay, now for our next unit conversion factor, what final units are we aiming for? Yep, micrograms. Okay, so we want micrograms on top. And what units do we need to cancel? Grams. Okay, perfect. So reading off from our equality, we know that 1 microgram corresponds to what power of 10? How many grams? Yep, 10 to the negative 6. Okay, perfect. So we have our long form unit conversion set up. So now all we have to do is enter it into our calculator. Oh, what if you borrow the calculator? Thank you. So let's break out the document camera and let's show how to do that. Okay, so first and foremost, we're going to have it in flow mode and we're going to enter our number. So in this case, we're going to enter 375. Perfect. So far, so good. We have next the power of 10. We're going to be multiplying by what power of 10? 10 to the negative third. Okay. So what we're going to do is we're going to hit the multiplication symbol, and then we're going to do 1 EE negative sign 3. And so this is what you get after your first operation. Now, looking back at our problem, what's our next step? What are we dividing by? 10 to the negative 6. Okay, so what we're going to do is we're going to hit the division symbol. Okay, we're going to hit the division symbol, then parentheses, 1 negative 6. Okay, we're then going to close the parentheses and then hit the equal sign. And in the end, you'll get quite a large number. To convert this into scientific notation to make it a little bit easier to write, we're going to hit the second key followed by the button number 5, which is the science function. And in the end, as our final answer, we'll get 3.75 times 10 to the 5th micrograms. Does that make sense to everyone? Yes. Okay, perfect. So let's keep going from here. In our next step, we're asked to convert composite units. So we're going from 160 milligram per microliter to kilogram per liter. And this time we're going to do this a little bit more efficiently now. So starting off, we have units of 160 milligram per microliter. Okay, so we're going from milligram to microliter, and our end goal is to reach kilogram per liter. Now, we're going to have to go through a few intermediate steps. So looking at the top of our unit conversion, what units are we going to go through? If we're going from milligram to kilogram, what's our intermediate unit? Grams. Okay, so we're going to go to gram per microliter. And now to go from microliter to liter, can we do that easily? Yes. Okay, so we're going to go from gram per microliter to gram per liter, and then finally kilogram per liter. Okay, so just showing our steps to help us design our conversion factors appropriately. Okay, so with that set up, we're now ready to begin. And let's write our 160 a little bit farther down so we have a little bit more space to work with. So we have 160 milligram per microliter. So in our first step, if we want to go from milligram to gram, what units need to be on top? Grams, okay? So how many grams do we have in 1 milligram? What's our equality? Yep, 10 to the negative third. Perfect. Okay, so we did our first step perfectly. Next, we're going from 1 over microliter to 1 over liter. So in order for these microliters to cancel, what units do we need to have on top? Microliters. They need to be on opposite sides of the dividing line. So in 1 microliter, that corresponds to how many liters? What does the micro prefix correspond to? 10 to the negative 6. Okay. Finally, so we've accomplished step number 2. If we want to go from grams to kilograms, what units need to be on top? Kilograms, right? If we want to go from gram to kilogram, we need kilograms on top. And what units are we trying to cancel? What units do we have sitting left over that we need to cancel? Grams. So what units need to be on the bottom? Grams. Okay, and we know that in 1 kilogram, there are how many grams? 10 to the third. Okay, perfect. Does that setup look familiar to everyone? We did a similar example in class, and there was also one on the pre-lecture quiz and homework. Now let's enter this into our calculator. Does everyone have this written down so we can enter this long form from our calculator? Okay. So first and foremost, let's set our calculator to flow mode, which is second and button number 4. We're next going to enter our number, which is 160. Okay. And in our first step, what power of 10 are we multiplying by? Negative 3. Okay. So we're going to do just that. So we're going to do times 1 negative 3. Okay. Perfect. So far, so good. What is our next step? What are we dividing by? 10 to the negative 6. Okay, so if we're going to our calculator, what we're going to do is we're going to first and foremost hit the division symbol, parentheses, then 1 EE negative 6. Everyone following so far in their calculator? Okay. Perfect. So we'll end up with the following number after the second step. Finally, what power of 10 are we dividing by? Yep, 10 to the third. So we're going to go to our calculator. We're going to hit the division symbol, parentheses, 1 EE3. Perfect. And when you're done with that, you push the equal sign, and we end up with a final answer of 160. So you did a lot of conversions, just end up back at the same point. So let's enter that in. So it's 160, and what are our final units? What are our final units? Kilogram per liter. Yeah, don't forget to put the units. Perfect. Any questions so far? Does this look familiar to our last lecture? Okay. Now, for our final set of conversions, we're going to be converting cubic units. Now, cubic units are relatively straightforward, except they have one gimmick associated with how you generate their conversion factors. So first and foremost, we are starting with units of kilometers cubed. Now, what units are we trying to reach? What's our target here? Millimeters cubed. Now, as we're going from a prefix to a prefix unit, what do we go through? What unit do we go through? Meters, or the base unit of meters. And instead of just meters, in this case, it would be meters cubed. Okay, perfect. So far, so good. Now, writing out our starting units, we have 457 kilometers cubed. Now, before we worry about this cube, let's just think for a moment. If we want to go, we're starting off in kilometers. What units are we trying to get to first? Meters, right? So what units need to be on top? Meters, okay? And what units do we want to cancel? Where are we going from? Kilometers. So what needs to be on the bottom? Kilometers. Okay. Now we know that in 1 kilometer, there are how many meters? Kilo corresponds 10 to the third, exactly. Now, if you're curious why I'm able to write these so quickly, remember the rule that we discussed last class session. Where does the power of 10 always go?
Or to the base.
To the base unit. You're always going to write your power of 10 with the base unit, and 1 will always be with the prefix unit. Yep, okay. Now, this conversion will only allow us to convert from kilometers to meters, but we have kilometers cubed. So what do we do to this conversion factor? Cube it, exactly. So we raise this entire conversion factor to the power of 3. Okay, let's repeat this process. In the next step, we're going from meter to millimeter. So what units are going to go on top? Millimeter, yep. Okay, and what units are going to go on the bottom? What units are we going from? Meters. Okay, good, good. So in 1 millimeter, we have how many meters? What power of 10 does milli? What was that? 10 to the negative third. Yep. And just like before, this allows us to convert from meters to millimeters, but we're dealing with meters cubed and millimeters cubed. So what do we do to this conversion factor? Cube it. Yep. Okay. Everyone okay so far? Are we ready to enter into our calculators? So let's get out our calculators and let's start. So first and foremost, we're going to enter 457. So far, so good. Next, what are we multiplying by? What are we multiplying by? 10? Sure, 10 to the 9th or 10 to the 3rd cubed. If you're really fast at dealing with powers of 10, you can compute out this cube by multiplying these two exponents together. So this is 10 to the 9th and 1 over 10 to the negative 9th. Let's show how you'd enter this longhand into your calculator just for practice. Okay, so we're going to take 457. We're going to hit the multiplication symbol. So you're going to hit the multiplication symbol, and then you're going to hit parentheses. So you're going to see a 0 pop up. You're then going to enter 1EE3 because we're dealing with 10 to the third, right? Next, we're going to cube it by hitting the second button, followed by the 1 key. And if you zoom in on the 1 key, there's a little cubed in green. You should end up with the following large number after your input. Everyone okay so far? You're then going to close the parentheses and hit the equal sign. Okay, so after our first step, we have 457 and this little exponent of 11 times 10 to the 11th. What's our final step in this process? What are we dividing by? 10 to the negative third cubed, or 10 to the negative 9. So let's show how we'd enter that in longhand. We're next going to hit the division symbol and then hit parentheses. You should see a 0 pop up. We're next going to enter 1EE negative 3 because we're dealing with 10 to the negative third. And what do we have to do to this conversion factor? Cube it. Yep. So we hit second, followed by 1 to cube it. And you should end up with a very, very, very small number. You then close your parentheses. And then to finish off the calculation, you hit the equals button. So you should end up with 4.57 times 10 to the 20th, a quite large number. Does that make sense so far? Okay, perfect. So let's report our final answer, and then we're done. Okay, so we have 4.57 times 10 to the 20th. Whoops, one moment. And then what are our units? What are our units? Millimeters cubed. Perfect. And that's the end of this set of unit conversions. You should be very comfortable doing unit conversions quickly, and you'll see a few more of these types of unit conversions on your pre-lab for the water analysis lab. Any questions before we move to our major lecture content for today? Okay, with that said, let's now move on to resuming our lecture discussion on significant figures and performing calculations involving significant figures. So, first and foremost, as we last left off our class session, we collect data primarily by taking measurements using instruments. And we discussed how to take various measurements using different types of instruments last class session. This class session, we're going to look at different measurements, different numbers collected throughout the course of performing chemistry and how to assess what digits are significant, what digits are not significant, and how do we handle numbers and calculations respecting significant figures. Okay, so let's talk about significant figures. A digit is significant. There are a few rules. First and foremost, non-zero digits are always significant. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of these digits are significant. It's a non-zero number, it's significant. Now, a 0 is significant if either of these two criteria are met. First, if it's between non-zero digits, for example, 0.505. So if we look at this 0, is it between non-zero digits? Yes. Ergo, it is significant. Okay? So we'd say that this has 3 sig figs. We'll talk about why 3 sig figs in a moment. The other criteria for when a 0 is significant, if it's at the end of a number and after a decimal point. Okay? So what do I mean by that? If we have, for example, 5.10, looking at this 0, is it at the end of a number and after a decimal point? Yeah. Everyone see the decimal point right here? Yeah. So this 0 is significant. So how many total significant digits do we have in this number? 3. How many do we have? 3. The 5 is significant, the 1 is significant because they're non-zero digits, and this 0 is also significant because it's at the end of a number after a decimal point. So this would have 3 sig figs. Now, let's discuss the cases when a 0 is not significant, and let's change pen color for that. So a 0 is not significant if either of these criteria are met. If it's before the first non-zero digit, for example, 0.05. So looking at these two leading zeros, are these two zeros before the first non-zero digit? Yes. So are they significant? No. So how many sig figs do we actually have in this number? 1. This only has 1 sig fig. I like to call these zeros, quote unquote, leading zeros. Now, the other case when a 0 is not significant is if it's at the end of a number, but not after a decimal point. For example, 150. Looking at this 0, is it at the end of a number? Is it before or after a decimal point? Are there any decimal points in this number? No. So then, if we don't have a decimal point, is this 0 significant? No. So how many sig figs does 150 have? 2. The 1 and the 5 are the only significant digits in this number. Does that make sense? Okay. So there is a special subclass of number that we need to pay special attention to with regards to counting significant figures. We call these numbers exact numbers. So conversion factors, or numbers obtained from counting without using an instrument, have unlimited significant figures. We call these exact numbers. So for example, if I counted the number of students in this class, and I note that there are 31 students. As I have not used an instrument, I haven't used a scale, a ruler, or any other device with an inherent uncertainty associated with it. And when we're counting objects, there's no way for there to be half a student in the class, right? And as a result, numbers obtained from counting, this 31 has an unlimited number of significant figures. It's considered exact. Another example that comes up a lot in chemistry is if we look at a molecule, how many atoms with the H symbol, how many hydrogen atoms do we see? 2. So we have 2 hydrogen atoms. There's no such thing as half a hydrogen atom. These are whole number quantities. And as such, this 2 has an unlimited number of sig figs. This is important when we start to use these exact numbers in calculations. The other example is a conversion factor. For example, we know there are 10 to the third meter is equal to 1 kilometer. So if we generate a conversion factor, conversion factors are also exact numbers. They will never limit the amount of significant figures you can report. Okay, so let's try to indicate, and let's look at each of the following numbers, and let's indicate the number of significant figures, and let's try writing the number in scientific notation. And I'll start us off here. So 5.07. So looking at this, we have a 5. This 0 is between non-zero digits, and it's after a decimal point, so this 0 is significant. 7 by default is significant. So this number has 3 sig figs, or 3 significant figures. This number is already, conveniently enough, in scientific notation. Why is it in scientific notation? Is 5 between 1 and 10? Yes. And you can technically try to write this as 5.07 times 10 to the 0, but we typically omit powers of 10 that are not. We omit 10 to the 0. It's unnecessary. So what I'd like you to do now is to take these 4 numbers, identify the number of significant figures, and then write them in scientific notation. And I'll be walking around to check to see how everyone's doing. questions? Any questions? Okay, looking at the second number, are those the second after 5.0? Are those zeros after a non-zero number? Are they just before any non-zero? Looking at those non-zeros.
So it would.
Exactly. Yes, yes. No. Exactly. Any questions? So are they after a non-zero number and after a decimal point? Yep. So they're significant. Any questions? Yep.
So the one you don't use it so we can have 60.
They have unlimited significance.
So that looks like 31.0.
Yes, like I said, they have nuclear and non-zero straight.
Okay, so only of that is 31.
You write it as 31, but you wouldn't count it as two significants. You count it as we'll talk about rules for how to do calculations with significants in a moment. But the main rule is if you're doing a calculation with an exact number, they're never going to limit your significance. Your other measurements will. Does that make sense? Any questions?
So,
Yeah.
for example, like we talked about,
Yeah.
meeting
Yeah.
zeros, so then that means you're just counting everything.
Yes, exactly.
Thank you.
Okay, so I saw a lot of reasonable answers. Let's elicit some class response here. So if we have 0.0000876, would someone like to volunteer? How many significant figures does this number have? 3. Yep, this has 3 sig figs. Looking at these zeros in front, are these zeros before the first non-zero number? Are they before the first non-zero digit? So these are leading zeros and they are not significant. So the only significant digits are these 8, 7, and 6, the 3 non-zero digits. Okay, if we were to write this in scientific notation, let's switch pen colors for this. How many spaces do we have to move our decimal point and in what direction? 5 to the right. 1, 2, 3, 4, 5. So we're moving 5 to the right. And as a result, we have 8.76. And if we move our decimal point to the right, is our exponent going to be positive or negative? Negative. So it's going to be, instead of 5, it would be negative 5. Okay, perfect. Okay, let's continue on. Let's try this next number. So we have 998.9877000. How many significant figures does this number have? Would someone like to take a guess? Let's see, 1, 2, 3, 4, 5, 6, 7. Definitely these first 7 digits are significant. So let's look at these zeros. Are these zeros after a decimal point?
Yes.
And are they after a non-zero number?
Yes.
So are they significant?
Yes.
Yes. So it would actually be a total of 10 significant figures. Okay, now in scientific notation, let's switch pen colors for this one more time. What direction do we have to move our decimal point? To the left or to the right? To the left. And how many spaces?
2.
Yep, 1, 2. So we're moving 2 spaces to the left. So is our exponent going to be positive or negative? Positive. So even though it may be tempting to truncate digits, all of these digits are significant. So when you write the number in scientific notation, you retain every single one of your significant digits. So this would be 9.989877000 times 10 to the second. Do not truncate significant digits. Does that make sense? Okay. So let's continue on now. Really quickly, would someone like to tell me how many sig figs are in this fourth number? 7. Okay, so let's count. So we have 0.0000009830000. Okay, looking at these zeros in front, are these zeros before the first non-zero digit? So are they significant? No. So let's put a little X. Okay, what about these zeros at the end, these trailing zeros? Are they after a decimal point? Yes. Since they're after a decimal point and they're after a non-zero number, are they significant? Yes. So we count 1, 2, 3, 4, 5, 6, 7. We have 7 sig figs. Okay, now let's try to figure out how this number would look in scientific notation. Would someone like to volunteer? What power of 10 are we dealing with for scientific notation? What was that? -7. Let's talk a little bit about why that is. Okay, so we have to move our decimal point to the right. 1, 2, 3, 4, 5, 6, 7. So we're moving our decimal point 7 spaces to the right. So we have 9.830000 times 10 to the -7th. We're dealing with a very small number. Does that make sense to everyone? Would someone like to volunteer this last example? 10200. How many sig figs does this number have? So if it had a decimal point at the end, it would have 5. But since it does not have a decimal point, looking at these zeros at the end, these trailing zeros, are these zeros significant? No. So then this number only has 3 sig figs. And we would write this as 1.02 times 10 to the 4th. Does that make sense to everyone? Just as a reminder, in case you're having trouble writing numbers in scientific notation, your calculator will do it for you. So let's show this. So first and foremost, let's enter 10200. Okay, so here's our long form number, right? Now you can do this with just a push of a button. You hit the second followed by the number 5, which converts the number into scientific notation. Conveniently enough, and one thing to do note about this, your calculator does not know what significant figures are. So when you're doing calculations using a calculator, you need to apply your sig fig rules and count sig figs on your own, because the calculator will just lop off the zeros. Does that make sense? Okay. So your calculator can do a lot of the work in converting numbers into scientific notation. So let's keep going if we don't have any other questions. Everyone good so far? Okay. So now that we know how to count significant figures, what we're going to do next is we're going to start applying significant figure rules to calculations. So as a general rule of thumb, there are some exceptions. The calculated value cannot be more precise than the measured values used in calculations. Let's show examples of this. So when you're dealing with calculations, in many cases, you're going to have to round numbers to the proper number of sig figs. You're going to have to round to a certain number of significant figures. So let's talk a little bit about the rounding rules. So for rounding, the first thing you're going to do is you're going to indicate the last significant digit. So whatever the last significant digit is, you're going to underline it, circle it, highlight it, whatever. Now, to decide whether you round up or down, you're going to examine the number immediately after the last significant digit. For example, if you have 457 and we decided based on our calculations that we only are retaining 2 significant figures, let's pretend this 5 is our last significant digit. What number are we going to look at in order to figure out whether we round up or down? The 7, the number immediately after
the last significant digit. So we're going to highlight our last significant digit. We're going to look over to the right. And the rules are you round down if the digit is 4 or less, and you round up if the digit is 5 or greater. So looking at 7, is 7 greater than or equal to 5? Yeah. So do we round up or down? Up. Okay. So that would give us 460. Now, one thing to keep in mind, make sure to respect the magnitude of your number. This digit doesn't disappear if you're dealing with a particularly large number and you're rounding. You need to hold this place using a 0, right? It doesn't turn into 46 just because you've rounded, right? Does that make sense? Okay. So let's look at a few examples now. If we're dealing with 13.5222 and we want to round this to 4 significant figures. So keeping that in mind that we're trying to round this to 4 significant figures, where is our 4th significant figure? The 2. Yep, the 2 immediately after the 5. Okay, we look over one space to the right. Is 2 greater than or less than 5? Yep, so do we round up or down? Down. So this would just be 13.52. And how many sig figs does this rounded number have? 4. And our target was 4 sig figs. So everything checks out. Let's do another example. This time we're going to take 13.6255 and we're going to round it to 5 significant figures. Okay, so let's change pen colors. So where is our 5th significant digit? So counting from the left to the right, where is the 5th significant digit? Yep, the first 5. 1, 2, 3, 4, 5. So this is our 5th significant digit. We look to the right, one space. So is 5 greater than or equal to 5? It's equal to 5. So do we round up or down? Up. 5 or greater, you round up. So this would be 13.626. And as we notice, this final number has a total of 5 sig figs as requested from our rounding operation. Does that make sense? Okay. So I'd like you now to attempt the following 2 examples and round the following 2 numbers to the indicated number of significant figures. So in this first case, I want you to round 1,350 to 2 sig figs. And in the second case, I want you to round 0.005804 to 3 sig figs. And take a moment to work on that, and then we'll come together as a group to discuss. Any questions? Yes, but when rounding the large numbers, do these placeholder digits disappear? How do we indicate that we have a large number? What do we put it in? Just like in our 257 example. Yep. Yes, yes. But it's just 1 0 enough. Is 140 the same as the 1,000? Yep, carry it. Sorry, I have a question. Yes, perfect. So I saw a lot of reasonable responses here. So looking at the first example, where is the second significant digit? What is the second significant digit? The 3, okay? So we highlight the 3 and we look to the right. Now my question to all of you is 5 greater than or equal to 5? Equal to, so do we round up or down? Up. Okay, so this would be 1,400. Remember, when you're rounding large numbers, you need to put placeholder zeros to account for the fact that this number is not 14, it's not 140, it's 1,400. You need to indicate the magnitude using placeholder zeros. Don't just get rid of the number when you're rounding. Does that make sense? Okay. In the next case, where is the third significant digit? Where is the third? Yes. Yes, that's exactly right. Okay, and as we look one space to the right, do we round up or down? So looking at 4, is 4 greater than or less than 5? Less than. So do we round up or down? Down, exactly right. So we have 0.00580. And how many significant figures does this number have? 3. This has 3 sig figs. The leading zeros are not significant. The trailing 0 after a decimal point and after a non-zero number is significant. So let's keep going. What we're now going to do is we're going to try multiplying and dividing numbers and accounting for significant figures in multiplication and division. So for multiplying or dividing numbers, the rule is fairly straightforward. Your final answer has significant figures equal to the number with the least number of sig figs. So you retain the least number of significant figures. For example, if you multiply 2.0, which has 2 significant figures, and you multiply it by 3.50, which has 3 significant figures, what is less, 2 or 3? 2. Right? We have 2 sig figs, that's the least number of significant figures. So how many significant figures do we retain? 2. Likewise, if you take 600, which has how many sig figs? 600 with no decimal point. 1, has 1 sig fig. And you multiply it by 5.0, which has 2 significant figures. How many significant figures do you retain? What's the least number of significant figures? 1. So how many sig figs do we retain? 1. So that's why we report our answer as 3,000, which also has 1 significant figure. Does that make sense? Let's do a few examples. This is best learned via application. And you really need to be careful that you're rounding things properly in a lot of these examples. So let's look at this first case. I'm asked to take 25 and multiply it by 4. Now, how many significant figures does 25 have? 2. Yep, it has 2 sig figs. How many significant figures does 4 have? 1. Okay, with that said, if I take 25 times 4, let's do that with our calculator really quickly. 25 times 4, that gives me 100. Let me do that one more time in clear view. 25 times 4, 100. Now, are we done here? Does my calculator give me the exact answer I need to report?
No.
Not 100%, because do calculators care about sig figs? No. So what you're going to do is you're going to perform the calculation in your calculator. You're going to write the number down. So in this case, we have 100. And now we need to check that it has the correct number of sig figs. And how many sig figs does 100 have? 1. Has 1 sig fig. So are we done? Do we have our final answer with 1 sig fig? Is that the least number of sig figs that we need to report? Yes. So we're only allowed to retain 1 sig fig because that's the least number of significant figures. Our answer has 1 sig fig, so we're done. There are cases where you will have to round to the appropriate number of significant figures. So I'm going to now let you loose on the following 4 problems and make sure you're counting your significant figures carefully here. And I'll be walking around to check to see how everyone's doing. Any questions? Any questions? Any questions? Any questions? Looks good so far. So this number is almost correct. So looking at this 0 at the end, is it the left 0 is considered? So you just get rid of 0.
Any questions? Yes, exactly. Yep. So then, only sig figs is your answer. That's the smallest of those two.
Yes.
Yep. Yes, exactly. Any questions? Any questions? Looks good so far. Any questions? Yes.
I get one of the
Yeah.
and one.
Yes, exactly right. So let's talk a little bit about these examples. So first and foremost, we're taking 2.59 times 2.0. Now let's count sig figs here. How many significant figures does 2.59 have? 3. Has 3 sig figs. How many significant figures does 2.0 have? 2. So then, how many significant figures does our answer need to have? 2. So we need 2 significant figures in our answer. Oops. Oops, one moment. Okay, perfect. So now let's break out our calculator and let's perform this operation. So we're taking 2.59 times 2.0, and we get out 5.18. Now we're not entirely done yet. We have 5.18, but we are now going to have to round this number to the correct number of significant figures. So 5.18, we're not entirely done. So what is the second significant figure in this number, 5.18? The 1. So let's highlight the 1 so that way we can all see that. So this 1 is the second significant figure. We look over one space to the right. Is 8 greater than or less than 5? Greater. So do you round up or down? Up. And we'd write this just as 5.2. 5.20 would have 3 sig figs. So this answer only has 2 sig figs as required. Does that make sense to everyone? Okay, let's continue on with this next example. So we have 2.000 divided by 3.0. So how many significant figures does our top number have? 4, yep. So we have 4 sig figs on top. How many significant figures does our bottom number have? 2, has 2 sig figs. Okay, so let's punch this into our calculator now. 2.000 divided by 3.0, and we get 0.66 trailing infinitely. Okay, let's write this number down. So we have 0.666. Let's just stick with the relevant number of digits here. So looking at our calculation, how many significant figures are we going to have to round to? How many significant figures do we retain? 2, exactly. The least between 2 and 4 is 2. So we want to round this to 2 significant figures. So my question to all of you is, where is the second significant digit? Is it the first 6 or the second 6? The second, okay? So let's put a box around it. Let's look one space to the right. Is 6 greater than 5? Yes. So do we round up? Yes. So that gives us 0.67. And this has 2 sig figs to its name. Oops, one moment. There we go. Does that make sense to everyone? Okay, let's keep going. We have 0.0505, and we're dividing by 5.000. So looking at this top number, how many significant figures does this top number have?
3. Has 3 sig figs. Because remember, these leading zeros are not significant. What about the bottom number of 5.000? How many sig figs does the bottom number have? 4. Exactly. Okay, so how many significant figures do we need to report in our answer? What's less, 3 or 4? 3. So we need to report 3 significant figures in our answer. So let's do this calculation in our calculator. So we have 0.0505 divided by 5.000. And we get the following answer, 0.0101. Okay, so let's write that down. So we have 0.0101. Is this number okay? Does this number have the correct number of significant figures? Yes. We want 3. This number has 3. We're good. Let's complete this final example. So if we have 650 divided by 1.00, how many significant figures does the top number have? 2. Has 2 sig figs. Trailing zeros that are not before or after a decimal point are not significant. What about 1.00? How many sig figs does 1.00 have? 3. Yep. Okay, so if we compute this calculation in our calculators, we will get 650. Are we good? And let's try to explain why. Looking at our sig figs, how many sig figs do we need to report? 2. We need to report 2 sig figs. Okay. Looking at 650, does it have 2 sig figs? Yes. So we're good to go. Now, a more proper way of handling significant figures is to write numbers in scientific notation because it's unambiguous. So if we took this number and wrote it as 6.5 times 10 to the second, is it abundantly clear how many significant figures we have? Yes, this is one of the benefits of scientific notation. It's unambiguous about counting sig figs. It gets rid of trailing zeros and it gets rid of leading zeros. So it's wonderful for performing calculations and following sig fig rules. Any questions on multiplication and division? Okay, let's keep going. We still have plenty of time. So, when adding or subtracting numbers, the rules are a little bit different. Instead of retaining and looking at the total number of significant figures, we instead look at the number of decimal places. Now, a lot of these significant figure rules are based on a concept known as instrumental error and experimental error. We don't calculate experimental error associated with inherent instrument uncertainty in this class, but these rules we'll see later on in more advanced chemistry classes when you start to quantify error and how error is carried through calculations. So, for addition and subtraction, we care about decimal places. So first and foremost, our first goal in this process is to write each number, and then we're lining up the decimal points. Now, if there is no decimal point, you're going to place a decimal point at the end of each number. Okay? We need a decimal point in order to deal with addition and subtraction operations. If both numbers do not have a decimal place, you're going to align the last reported significant digit. Don't worry about that for now. Next, just like before, we're going to indicate the number with the least decimal places. Once you have that established, we've counted our number of decimal places, you add or subtract the numbers. You just punch it into your calculator. Finally, you round the calculated result to the lowest number of decimal places. So remember, when adding or subtracting, you retain the least number of decimal places, not significant figures. So decimal places are the name of the game here. So let's look at a few examples. So let's look at these two representative examples. In this case, we're adding 22.4132 and 11.3. So we've lined up our decimal points. And now my question to all of you is, how many decimal places does the top number have? Not sig figs, decimal places. How many numbers after the decimal point? 4, right? 1, 2, 3, 4. So we have 4 decimal places. Looking at this bottom number of 11.3, how many decimal places does it have? How many numbers after the decimal point? 1. So it has 1 decimal place. So then, how many decimal places should our final answer have? 1. We retain the least number of decimal places. This is not the same as sig figs, decimal places. Okay, for example, let's look again at this next example. We're taking 3.000. How many sig figs does 3.000 have? 4 sig figs, and how many decimal places does it have? 3. Has 3 decimal places. Okay, looking at the bottom number of 175.2. How many decimal places does this number have? 1. Has 1 decimal place. Decimal places are different than the total number of sig figs. So then, based on this logic, what is the least number of decimal places? How many do we retain? 1. We retain 1 decimal place. Does that make sense to everyone? So let's keep going with this, and let's talk a little bit about a few representative examples. So let's tackle 5.56 minus 0.5. So how many decimal places does our top number have? 2. Has 2 decimal places. Okay, how many decimal places does our bottom number have? 1. Has 1 decimal place. So if we punch this into our calculator, 5.56 minus 0.5, we get 5.06. So let's enter that into our calculator. 5.06. Now, is this number 100% correct? No. How many decimal places does this number need to have? 1. So we need to round this to 1 decimal place. So looking at 5.06, where is the first decimal place? The 0. Okay, so we're going to highlight the 0. We're going to look 1 space to the right. And do we round up or down? Up. So we're going to round up to 5.1. This answer has 1 decimal place. Does that make sense to everyone? Okay, let's repeat this process for the following example. So 605 and 105. How many decimal places do each of these numbers have? Do they have any numbers after the decimal point? No. So we're going to put a decimal point at the end of each of these 2 numbers. And how many decimal places do each of these 2 numbers have? Are there any numbers after the decimal point? No. So we're going to write them as 0 decimal places. So these both have 0 decimal places. So how many decimal places are we going to retain? 0. Yep. So let's punch this into our calculator now. So we have 605 minus 105, and we get a grand total of 500. Now, my question to all of you is, do we put a decimal point at the end of this number? So let's think very carefully about this. Looking at both of these numbers, we have digits in the 1 place, and we have no decimal places. So do we retain this decimal point? Do we put a decimal point at the end of 500? So let's look and see. So looking at 500 dot, does 500 dot have 0 decimal places? Yes? does it have a number in the ones place? Is this number in the ones place significant? Do we have a significant digit in our ones place? Yes. So then, should we treat this 0 as significant if we're retaining the same number of significant decimal places? Yes. Does that make sense to everyone? Okay. If there is a significant digit in a decimal place, be it the tenths, the ones, the tens, or the hundreds, you have to make sure you're retaining the least number of significant decimal places. Okay, let's do another example. 1.07 minus 0.55. How many decimal places does 1.07 have? How many numbers after the decimal point does it have? 2. Has 2 decimal places. What about 0.55? 2, yep. Perfect. The fact that there's a decimal point here makes things so much easier. Okay, we're going to punch this into our calculator now. We have 1.07 minus 0.55, and we get out 0.52. Are we good to go? Is 0.52 permitted? Let's check. So looking at 0.52, does 0.52 have 2 decimal places? Yes. Now, this last question is actually quite tricky, and I'm going to show you a shortcut or a more consistent method to deal with adding and subtracting large numbers. So we'll discuss this example below. Any question on the basic addition and subtraction rules? No, the reason why we're going over this in so much detail is you're expected on your lab reports to follow all of these significant figure rules, and points will be deducted from your report if I catch any errors in reporting significant figures, both in measurements and calculations. So, with that said, let's talk about how to deal with large numbers without a decimal point. So, the rules are quite simple. First and foremost, you write the largest number in scientific notation. So your goal is to write the largest number in scientific notation. Now, this second step sounds a bit odd, but it ensures consistency. What you're going to do is you're going to write the other number in base 10 notation with the same power of 10. So essentially, we're going to make 2 numbers with the same power of 10. Finally, you just add or subtract both numbers, noting the number of decimal places. Okay, so let's show how this works here. So 1750s, or 1750. If we want to write this number in scientific notation, we put our decimal point at the end, and how many spaces do we have to move the decimal point to the left? 3, yep, 1, 2, 3. So this gives us 1.75 times 10 to the third. And my first question to all of you is, why did I get rid of that 0? Why did we get rid of that 0? It was not significant. Exactly right. Notice, is this a trailing 0? So this number as written is only conveying 3 sig figs. Okay, so this number has 3 sig figs, and how many decimal places? How many numbers after the decimal point? 2. Yep. Okay, now our new goal is to take 560 and get some number times 10 to the third. So to get the same power of 10, we're going to put our decimal point at the end, and how many spaces are we going to move it to the left? How many spaces are we going to move it to the left? So 2 would get us a number in normal scientific notation. That is correct. But if we want 10 to the third, how many spaces did we have to move our decimal point? 3. Yep. So we move it 1, 2, 3, and that gives us 0.56 times 10 to the third. Okay. Again, Why did I get rid of this 0? It's not significant. Exactly right. Any questions so far? So, as long as you have two numbers with the same power of 10, you can add and subtract them just like normal numbers. As a consequence, how many decimal places does 0.56 have? 2, right? Just pretend this 10 to the third didn't exist. Now we're just adding and subtracting two very simple numbers, right? Have we done this exact calculation before or something very similar? Have we added or subtracted numbers that look a little bit like this before? Yep. So all we have to do is punch it into our calculator. So we take 1.75 minus 0.56, and that gives us 1.19. Okay. So all we have to do is enter 1.19 and then include the power of 10 times 10 to the third. Does our final answer have the correct number of decimal places? Does it have 2 decimal places? Yes. So if we expanded this out, we get 1190. Now, just as a quick observation, what is the last place in both of these numbers that has a significant digit? What is the last reported significant place? It's not the ones, right? We have a 0, but what do we call this place after the ones? The tens place. And as we notice, where's our last significant digit in our answer? The tens place. Now, I personally find the method of writing numbers in base 10 notation easier, because if you're just looking at this number and assigning the last significant place, it can get a little bit tricky. When you have numbers written in pseudo-scientific notation and scientific notation, it's easier to identify the decimal point and just count decimal places. Does that make sense to everyone? You won't typically encounter calculations like this because most of the measurements you'll be taking in this class will have clear defined decimal points. I just wanted to show you this because this may pop up on some homework questions. Any question? Yes? Oh, yes, yes. And this isn't to make the subtraction easier. It's to make the significant figure counting easier. It's due to the fact that, yes, we can see the last reported significant place is the tens place, but another way to think about it is both of these numbers have 2 decimal places in this base 10 notation, so we retain 2 decimal places. If you're comfortable, you can just straight subtract these and note the tens place is the last significant place. But I find students often make mistakes in these calculations. That's why I'm pointing it out. Mm-hmm. Any other questions on addition and subtraction? Let's now try to do a few examples. So I'm going to start us off with this first example, and then you will continue on with the remaining examples. So we're taking 1.67 minus 0.71. So looking at both of these numbers, how many decimal places do both of these numbers have? 2. Both of these numbers have 2 decimal places. Why do we care about decimal places? We are subtracting numbers, right? So our next step is to punch this into our calculator. So we have 1.67 minus 0.71. And we get, as our final answer, 0.96. Now, does anyone notice something a little bit funny about this answer? There's nothing wrong with it inherently, but notice how we started with a number with how many significant figures? 3. And how many significant figures does our answer have? 2. This is not uncommon. When you add or subtract numbers, you can quote unquote gain or lose sig figs in some cases. As long as you're following the significant figure rules for each step, you're in the clear. Okay, with that said, I'd like you to attempt the next batch of examples. I have 3 examples slated, and if you have the note set printed, there's a 4th example set below question 4. So I'd like you to attempt these 3 examples, and then we'll come together to discuss. Any questions? Any questions? Everything going okay? Yes. Is it okay if we talk about this? Send me an email, we can talk about this. Okay. Michael mentions. And all mentions.
Oh.
Yep. Yep. Yeah. Any questions? Everything going okay? Everything going okay? Any questions? Everything going okay? Looks good so far. Everything going okay? I see a lot of reasonable answers. People are getting much faster at this. So let's, for the sake of time, let's start looking at questions 2 through 5. So first and foremost, looking at 5,300 minus 700. Now, trying method number 1, what is the last place that contains a significant digit? So looking at this, does the ones place in either of these numbers have a significant digit? No. What about the tens place? No. What about the hundreds place? Yes. So in both cases, the hundreds place has a significant digit. So we are going to retain up to the hundreds place. If we're using the scientific notation method, we'd be taking 5.3 times 10 to the third minus 0.7 times 10 to the third. Again, why did I get rid of these zeros when I wrote my numbers in scientific notation? Are those zeros significant? No. And that's what this method really tries to explicitly indicate. What digits are significant, what decimal places are significant, and which ones are not. So if we punch this into our calculator, 5,300 minus 700 gives us 4,600. Okay, so let's write this. So 4,600 or 4,600. Does it limit its significant decimal places to the hundreds place? Do we have a digit only in the hundreds place? So let me rephrase. So we're allowed to report digits up to the hundreds place, right? We've reported a digit in the hundreds place, right? Did we report any significant digits past the hundreds place? Are these zeros significant? No. So this number has the correct number of significant decimal places. I personally like the scientific notation method because it's much easier to see this. For example, 5.3 has how many decimal places? 1, right? We have 1 decimal place. 0.7 has how many decimal places? 1. So how many decimal places do we retain? 1. And that gives us 4.6 times 10 to the third, which is the exact same number as 4,600. Is this example much easier for us to see and count decimal places? Yes, this is why I like it. Okay, let's keep going through these examples. And I'd like some class input on this. So 50.4 minus 5.46. So my question to all of you is, how many decimal places should my final answer have? 1. This top input has 1 decimal place. This bottom input has 2 decimal places. The least number of decimal places is 1 decimal place. So our answer should have 1 decimal place. Wonderful. Let's punch this into our calculator.
So we take 50.4 minus 5.46, and that gives us 44.94. Are we done? Can we just read off our calculator and call it a day? No. Okay, perfect. So we have 44.94. And how many decimal places do we need to round this number to? 1. We need 1 decimal place. So now let's switch pen colors now. Our first decimal place is in the 9. We look 1 space to the right. Is 4 greater than or less than 5? Less than. So do we round up or down? Down. So that gives us as our final answer 44.9 with 1 decimal place. Does that make sense to everyone? Okay. Looking at time, we're out of time for today, but we'll continue this next class session. Please make sure to complete the pre-lecture assignment for Thursday, and please make sure to print out the Chapter 2 revised notes.